Today we are going to talk about the fact that AI is different than chatbots. I really wanted to do this video, and I came back to YouTube after 5 years of silence, and I've noticed that there are plenty of newcomers whose ideas are very confused. So let's talk about this today, and we'll go through some visual examples, and we will dive deep into what AI really is. All right, so I think that is kind of funny how in the last couple of years, the word AI has basically been replaced by a chat window, right? So you say, I work in AI, and people immediately think, okay, so you build chatbots like ChatGPT, right? And if they are slightly more informed, they may say something like, so you work with LLMs, large language models. Now, in this video, I want to push back on this idea. I want to show you that there is much more to AI than just chatbots. I will do it with a simple picture, a few boxes on this blackboard, and we will have a quick tour of the main ideas that live inside the AI box. Okay, let's start. So I will draw this large box that is the AI box. Now inside the AI box, we have a smaller box that is the neural networks box. Inside the neural network box, we have an even smaller box that is large language models. This is the engine of modern chatbots. Okay. Now, I think that this picture already gives you a hint of what I'm going to talk about today. And the picture is quite clear. We have this large box that is the AI box. Very loosely, it's all the techniques that try to make machine do things that if a human did them, we would call them intelligent, like planning, perceiving, learning, reasoning, decision-making, playing games, and so on. Now, inside the AI box, as you can see, I've drawn this neural network box, and neural networks are models built from many layers of simple units that we call neurons that are trained on large data sets, and they have been incredibly successful in things like image recognition, speech and language. Now then, inside the neural network box, I've drawn this LLMs box, and these large language models, the engines of chatbot. So the picture is pretty simple here. We have the big box, AI, medium box, deep learning or neural network, and then tiny box is large language models and chatbots. Now, I think you can already see the point that I'm making here. AI is not equal to LLMs, right? So LLMs are just a subset of a method that lives inside the AI box. All right. So what else there is inside the AI box? Today we are going to talk about 7 other additional boxes other than the neural network box. I'm just going to give you a brief description of each one of these boxes. So first of all, let's draw these 7 boxes. So we can start from here, and then we will talk briefly about each one of them. All right, let's start with box number 1. Box number 1 is going to be search and planning. Then in box number 2, we're going to talk about symbolic reasoning, and more in general, esper systems. In box number 3, we're going to talk about Bayesian methods, and more in general, probabilistic methods. Box 4 is Gaussian processes, and more in general, kernel methods. Box 5 is going to be classical machine learning methods like support vector machines, or K nearest neighbors, and so on. Box number 6 is going to be reinforcement learning. And finally, box number 7 is going to be evolutionary methods and genetic algorithms. All right, so that starts with the first box, search and planning, search and planning. All right, so search and planning are about finding sequences of action that when you take it, are going to take you from point A to point B. Okay, so we have point A, point B. Now you can imagine that there are different routes that can bring you from A to B. So one can be this one. One could be this one that goes through C and then leads you to B. There could be another one that goes through D, it goes to E, and eventually you can reach B. Now the idea is pretty simple, and if you imagine a robot in a maze, or Google Maps trying to find the best route between two cities, or a chess engine that is searching through possible moves, then you can understand what is search and planning. The core idea is quite simple. You have a state, you have actions, and you need to explore this tree of possibility efficiently, right? So classic algorithms here are A star or geometry searches that are used to play chess and Go, for instance. Now, the important point is that these systems, they don't need a chat interface, right? They don't need language. They don't need even a neural network. But they are still very much AI because they are making decisions about what to do next in this complex space. All right. Now, second box are symbolic AI, let's call it, and expert systems, okay? Now imagine a statement like this one. If fever, then flu, okay? We have logical operators here, and these are mini symbolic system, expert system. Of course, we can have much more complicated statements. Imagine if A and B and C, then D. Okay, as you can see, we have more logical operators here, and these systems were very popular in the 80s and 90s, especially in medical diagnosis, configuration of complex products in various industrial settings. Now, the nice thing about symbolic system is that they are explicit. You can inspect the rules, you can see exactly why a conclusion was reached, and you can add or remove knowledge by simply editing the rules. Now, today they are not fashionable on social media, but they are still used in many places where you want a deterministic, explainable behavior. Now, once again, these systems live entirely outside the deep learning box, LLM box. They don't need any chat interface, but they are still very much AI. Okay, third box are Bayesian methods. And more in general, probabilistic methods. Okay, now imagine the following graph. You have two nodes, and you have a directed arrow connecting the two nodes. The first node is rain. The second one is traffic. Rain causes traffic. Now, of course, you may have much more complex graphs. This, by the way, is a mini Bayesian network. The core idea here is that we want to embrace uncertainty, and we want to treat everything as a probability. Now, in the Bayesian mindset, you start with some prior belief, then you observe, you see new evidence, and you update this belief. Now, for example, we can ask, what's the probability of a traffic jam given that it's raining? You can make this arbitrarily more complicated. For instance, you can say what's the probability that it's raining, that there is traffic, given that it's raining, it is Monday, and it's 8 a.m. Now, Bayesian networks are graph like this one. The nodes are the random variables, and the arrows represent dependencies between these variables. Now, they were and they still are used to model complex systems where lots of uncertain factors interact. You can think about medical diagnosis, fault detection, risk assessment, and so on. Inside this category, there are also Markov models, hidden Markov models, and you can still consider this like a chain. And in the past, they were the backbone of speech recognition, language modeling. So before deep learning and before large language models, if you were working in language modeling and speech recognition, you were probably using one of these models, hidden Markov models, more likely. Now, this box is interesting because it encloses a series of methods that are rigorous, mathematical, they are extremely powerful. And once again, there is nothing to do with chatbots per se. I've been working with this model for quite a long time, both in the University of Edinburgh, University of Cambridge. So maybe we can have a deep dive at some point about these methods. All right, box number 4 is going to be Gaussian processes, and more in general, kernel methods. Okay, what are Gaussian processes? They sit at the intersection of Bayesian thinking and function approximation. Now, very informally, a Gaussian process is a way to put a probability distribution over functions. Now, instead of saying, this is the function that fits the data, you can say, here is a whole family of functions that could explain the data. And here is how probable each one of these functions is. Now, the result is that when you make a prediction, you don't just get a point estimate, you also get uncertainty. Imagine that you have a Cartesian plane like this. So Gaussian processes are going to give you a mean, and they're going to give you a uncertainty around the mean of this function, okay? Represented as these bands around the mean. Now you can draw from this so you can draw a function from this sort of probability distribution over functions. Gaussian processes are also used in a variety of fields like Bayesian optimization, where you have an expensive experiment or a simulation and you want to choose the next point to evaluate. You want to do it in a smart way. They're also used in time series modeling and in many scientific applications where uncertainty really matters, like in physics. And they're also quite used in finance, for instance. Now, once again, this is inside the AI box, oftentimes outside of the neural network and deep learning box, but yet they are extremely useful in real-world scientific and engineering applications. All right, box number 5. Now, this is a collection of methods that I called classical machine learning. Now, you can imagine that support vector machines are part of this class of classical machine learning methods. You may have k nearest neighbors in here. You can have decision trees. You can have a random forest, and so on. Now, of course, we can add other methods inside this box, like gradient boosting, logistic regression, and so on. They are the same old friends that you learn basically in initial classes of a machine learning course. Now, these models are still incredibly important. They are especially important in tabular data, for instance. Imagine all the type of data that are used by banks, insurance companies, hospitals, online shops, and so on. Every time that there are rows and columns, transactions, customers, metrics, these type of methods are very well suited to solve this type of problems. Now, a huge amount of applied AI in industry today is still built on top of these classical methods. They are simple to train, easier to interpret, and often they are perfectly sufficient for tasks like fraud detection, chart prediction, or basic recommendation. So while social media is obsessed with huge language models, a lot of real money is made by models that fit in a few lines of scikit-learn. All right, 6. Reinforcement learning. So, reinforcement learning, you can think of reinforcement learning by examining this very simple setting. So imagine that we have a chessboard like this one. And on this chessboard, we have a piece that we are going to call an agent. And this agent has a series of actions at its disposal to move in different locations of this chessboard. For instance, it can go up, down, left, and right. Now, typical flow in reinforcement learning is that you have an agent, our piece in this case, you have an environment, the chessboard, you have a series of actions, and then the agent can perform at every time step an action, and this action will generate a reward, and it will bring the agent to a new state. So typically you have state, action, reward, next state, and then you go back to the new state, or you repeat this cycle. So the core idea here is that you have an agent that interacts with an environment, it observes a state, takes an action, receives a reward, and then moves to a new state. Over time, the goal here is to learn a policy, a way of acting in the environment that maximizes the long-term reward. Classic examples here are playing Atari games, AlphaGo, that is learning to play Go at a superhuman level. In robotics, you want to teach a robot to walk or to manipulate objects, and so on. Now, many of the famous systems that we see today, they use deep neural networks, and they use it as a function approximator inside this RL framework. But the framework itself is independent of deep learning. The function approximator can really be even a table or a linear model. So conceptually here, we want to learn a behavior over time. And this is, of course, not about chatting or texting. It's all about feedback, exploration, and control. All right, box number 7, evolutionary algorithms. Now, this is a class of methods that contains many submethods, such as genetic algorithms, for instance. The idea is pretty simple. You have a population of candidate solutions. You can think of them like genomes, for instance, in the genetic algorithm metaphor. They are genomes, blueprints. And then you are taking this population and you apply operations like mutation or recombination to generate a new generation of candidate solutions. For instance, imagine that you have organism A, you have organism B. They are different solutions to the same problem. And imagine that it can have an offspring, and this offspring is going to be half green and half red. So the offspring is going to be a different solution that is a hybrid of the two parents' solution. Now, what you do in practice, you evaluate each candidate, you keep the best ones, you evaluate based on a function that is called fitness. Now you generate new variations, you repeat over many generations, and then the solution that is obtained after each generation is going to be better and better. Now, these methods are used for a variety of things, like designing structures and components in engineering, or automatically searching for good neural networks architectures or weights in neural evolution. They are used for solving optimization problems where gradients are not available. So when you cannot use neural networks, you can use evolutionary algorithms. Of course, there is an entire set of other methods within this larger box. but we don't have time to talk about them. Nevertheless, they are very interesting methods. So it would be interesting in a future video to talk a little bit more about them. Also because I was working with genetic algorithms quite a lot during my master's degree many years ago. Then there is also the final box. So let's switch back to green. So the final box, of course, is the box of neural networks, right? It's the box where we started from. Now, neural networks are not just large language models. They are not just LLMs. You may be familiar with things like convolutional neural networks that are used for vision problems, or recurrent neural networks that were used quite a lot before large language models came in, and they are still used today in a variety of problems, especially in reinforcement learning. And so my point here is that inside the neural network box, where we have the large language models, there is also a variety of other architecture that will be interesting to explore. So we can go back now to the beginning of the video, to our larger box here, the I box, and we can recap. So as you can see, we have seen that the larger box is the I box. Inside the I box, we have a variety of methods. Of course, this was just a subset of all the methods that are inside the I box. We didn't have time to talk about many other things like multi-agent system, robotics, computer vision, speech, human-AI interaction. We have a bunch of other boxes that are inside the I box, or they are intersecting the I box, that would be very interesting to talk about. Of course, the whole sense of this conversation is that AI is not chatbots. Okay, this is the beginning and conclusion of this video. So I hope that you got the sense of this video, and in the next videos we can go deeper into one of those boxes, start to talk a little bit more in details about one of those boxes, and it would be very useful if you can write in the comment below which one of these boxes you think I should talk about in the next video. But for the moment, that's it. Thank you very much for watching. Subscribe and like the video. This will be very useful to spread the word. And I will see you to the next one.